Last time on my previous video, we looked into Boyle's law, Charles' law, and Gay-Lussac's law. Now, with this one, the whole idea behind it is that it's looking at pressure, volume, and temperature, meaning that moles are going to be kept constant. We're not adding any more gas. We're just changing the conditions that they are under. It's all about change. So going from an initial to a final value. So how do we kind of combine all these three laws together? How exactly does that work? Well, this is where I'm going to get a little mathy on you. How are we going to combine them? Well, the idea is if I take the original formulas we have, so if I first start with Boyle's law, what we are going to do is we're going to fold in the other formulas. So meaning that I'm going to take Boyle's law, multiply it by Charles' law, and then multiply it by Gay-Lussac's law. So let's do the first one. So if I take Boyle's law, multiply in Charles' law, what we are going to do is we're going to bring it in on both sides. So when we do that, you can see that, okay, these are going to get multiplied. Now, if that's happened, we're going to combine like terms. So as you can see, the V1s are the same. So when this gets brought down, what we're going to have is P1 V1 squared T1, and then it's a very similar story on the other side. We'll have P2 V2 squared, because they're like terms, they get multiplied, so these are getting multiplied, and then T2. Next, we're going to fold in the next law, which is Gay-Lussac's law. So when we have that, we're going to multiply that too. We're going to take both of them, put them on both sides. We're going to, once again, put those in parentheses. And we're going to combine like terms again. Notice how the pressures are the same, and so are the temperatures. So what are we going to end up getting is we'll have P1 squared, V1 is still squared, T1 squared is equal to P2 squared, V2 squared, and T2 squared. Oh man, this is an interesting problem. So how do we simplify this? How do we get rid of squares? Well, we use a square root. So when we do that, we'll square root both sides, and this leads to our combined gas law, which will be P1 V1 over T1 is equal to P2 V2 over T2. This is our formula. So this combines all of them together into one giant formula. So this is the combined gas law. It is a powerful equation that allows us to be able to incorporate 3 of our 4 variables. So pressure, volume, temperature. Moles are constant, so they are not in this equation. We don't worry about them. It's all about change. So what kind of problems would you see with something involving this much change? So if I look at this first example, if you have a 10-liter balloon at standard temperature and pressure, okay, so this goes back to the first video of what the heck is standard temperature and pressure. So whenever you have STP, that's defining a specific condition. So we had our volume it mentioned at the beginning. STP tells you what the pressure and temperature are for an ideal gas, for how can we do simple calculations. So 1 is the pressure at sea level, which is 1 atmosphere. And then the temperature for the Kelvin scale, how to convert it from Celsius, is 273. So that's the temperature that's used. Now it says the pressure is increased. Okay, so we're taking that pressure, that is increasing. So P2 is going to 2 atmospheres. And that I got from right here in that equation. Then we also have that the temperature increased to 300 Kelvin. So T2 also increased, and that equals 300 Kelvin. Now the question is, what is the balloon's new volume? So the one thing we don't know is we have no idea what the volume is. So let's take our equation that we defined earlier, and what we're going to do is we're going to get V2 by itself. It's easier to rearrange the problem first than to just start plugging numbers in. That's usually when the most calculator errors occur. So rearrange first. It's doing just multiplication, division to rearrange. It always looks scary, but I promise you, practice it. It will get easier the more you do it. So we're trying to get V2 by itself. So how can we do that is we can multiply by the inverted equation of P2 and T2. So how can we look at this equation? So being that V2, let's move things around, is what we're interested in. The way we can kind of write that is instead like this. So P2 and T2 times times volume, right? So in order to cancel these, well, we just got to multiply it by its inverse. So what that causes is this to cancel this and temperature to cancel temperature. So we multiply both sides, and what we will get is T2, P2, and we will get our new equation that we can use for volume. And you can write this down if you're a little nervous about deriving things. It's something that you can use. So we have our new equation, and what we're going to do is we're going to plug in all of our values into this. So what it's going to end up being is we'll take our P1, which was 1 atmosphere, times that by V1, which was 10 liters, and then times that by T2, which was 300 K. That's our numerator, or what's on top. And then P2 and T2 were 2 atmospheres times, oh, I just realized I have T2 twice. So, and then it's going to be times by T1. Sorry about that. Notice there was a little typo there. So that should be T1. That'd be times 273 Kelvin. All right, and that's on bottom. So we'll take 1 times 10 times 300, solve for that, then divide by 2 times 273. Now when we get this, we'll get our volume, which in this case, you will get a volume of 5.49 liters as your answer. And that's how you use the combined gas law. Now let's try another one, because this is one I think that there are several ways to solve. There's many variables. So how else could you use it? Well, for this one, let's say if I have the volume of a container is increased from 100 milliliters to 425 milliliters. So what it's telling you is we have 2 volumes here. And there's the keyword 2. So when we are looking at this, right, we have a V1 and a V2. So let's write those down. We have an initial volume of 100 milliliters, and that's increasing to a final volume of 425 milliliters. And it says that causes the pressure of the gas to increase from 500 millimeters of mercury to 1200 millimeters of mercury. So we have also a P1 and a P2. All right, so we'll write those down for ourselves. And then we also says that it starts at an initial temperature of 300 K. So this is a helpful method for ourselves. Identify all the important piece of information, so that way you don't have this big word problem staring you at the face when you're going through this. Go through it slowly, identify it, make it simple for yourself. So when you're going through this, we are noticing all the important pieces, and we can see that, okay, what is it asking me to do? Well, you can identify you have 5 out of 6 variables. The missing piece is, what is the final temperature? So we want to know, what is T2 in all this, right? T2 is our missing piece. So let's try to look at our formula and see, can we get T2 by itself easily? Now, one thing you might have saw in my previous video was Oh, T2 is on the denominator. Is there an easy way to get this by itself? This is where we'll invert it. We're going to flip. So we're going to flip it. I don't know why I'm using highlighter there. But we're going to flip this. Then we're going to flip the script. So when we flip it, what that's going to become is T1 over P1 V1 is equal to T2 P2 V2. This allows for T2 to be by itself a little bit faster, so you are taking the inverse when you do this. So what we're going to do is multiply both sides by P2 V2, and what that's going to do is get that T2 by itself. Those cancel out, and we'll have our new formula, which will be P2 V2 T1 P1 V1 is all equal to T2. All right, we have a lot of variables to plug in here, so that's what we are going to do. We're going to plug all those in. And sorry, I kind of zoomed out here for a second, but I want to see all the variables. So pressure 2 was 1,200 millimeters of mercury. Volume 2 was 425 milliliters. T1 was 300 K. And that's all going to be divided by P1 and V1, so your original values. So that's 500 millimeters of mercury times 100 milliliters. Okay, so those are all of our values when we are looking at these. And we are going to solve for the top. So it'll be 1,200 times 425 times 300, solve, and divide by 500 times 100 in parentheses. So when you get that, you're going to get a massive temperature. You get a value of 3060 Kelvin as our temperature. So it says when all those are increasing, because we have in this problem that volume increases and pressure increases. They're typically inverse of one another. That does not commonly happen. So because of all that, well, it's something that the temperature needs to compensate. So the temperature skyrockets as a result. Okay, our last major law for now, for in terms of change. So our last law in terms of changing. Avogadro's law is all about avocados, right? So Avogadro or Avogadro's law, as we kind of like to joke around here about that, is all about volume and moles. So, and it's a really simple one. Let's say if you take a balloon and it's empty, right? So it has 0 moles of gas in it. You blow into it, it inflates. The moles of gas increase. You blow into it more, it gets bigger. The moles of gas increases. So with this one, it's all about how much are you blowing up a balloon? How much bigger are you? So as you add moles, it's going to be increasing in size, meaning volume increases. If you suck out the balloon, it decreases in size. Moles are also decreasing. So if we want to do a problem with this, it's a simple one to end on, is if I have 6 liters of gas, so that's our initial volume, and it contains 0.847 moles of gas, and what will happen, what will be the new amount of gas, so we want to know what N2 is, if the quantity is decreased to 3.80 liters. Okay, so what exactly are we looking at when that happens? Well, we're going to be plugging it into our equation. So when this one, we had our equation was V1 N1 is equal to V2 N2. So we need to get N2 by itself. So once again, we can do the same trick from before, right? We could move some things around. We could also arguably use the other equation I had up here, which was V1N2 is equal to V2N1. It's rearranging it. So we could do a couple different things. So when we rearrange that equation to figure out what is N2, what we need to do is divide both sides by V1. So it's going to be V2N1 divide by V1. So when we have that, what that's going to look like is V2N1 divide by V1. Okay, so if we plug in our values, we have 3.80 liters multiplied by moles, which is 0.847 moles, and that's going to be divided by 6 liters. And this is something that's predictable, right? As we look across, we can see volume is decreasing. So what should happen to the number of moles? They should also be decreasing. So when we solve for this, what you're going to be getting as a final answer is that you're going to have 0.424 moles of gas that's going to be forming. And that's our final answer for this problem, is that the gases are going to be decreasing. So the volume is decreasing, moles are decreasing. I hope that this video helped. This is going through the last equation regarding change. There are still more gas laws to come involving the ideal gas law, which will have probably at least 1 or 2 videos going through those. So please like and subscribe to have more content to be able to help you pass your chemistry class and for you to do the best possible. I hope to see you again in the future, and this is Dr. Dan, and it's been a pleasure to help you with chemistry. I'll see you all later. Bye.